In this lesson, we're going to introduce our mathematical equation for the magnetic force. And you can see right away that the magnetic force is given by QV cross B. And we are not looking at this from a theoretical point of view. We are treating it as an empirical formula that experiments have shown that this equation holds. So this is the equivalent of our F equals QE, right? When we had the electrostatic field, we said F equals QE. Now we have F equals QV cross B. And just like with F equals QE, the Q in that equation was the Q that was being affected by the electric field. And now the Q in F equals QV cross B, and again, please make sure you annotate this this page of notes carefully, because the Q in this equation, right, is the Q that's being pushed or pulled. It is not the source Qs of the external magnetic field. So we're just taking for granted that the external magnetic field is there, like the Earth's magnetic field, right? So there's a magnetic field present. Yes, there are moving Qs that make that magnetic field, but the Q in QV cross B is the charge that's been injected into the magnetic field. And why do I say injected? Because notice it's QV cross B. If you don't give the charge a Q, then you don't get a magnetic force. So not only do moving Qs make magnetic field, it is only moving Qs that are affected by magnetic field. Wow. Okay. Fundamentally, and this is one thing that makes magnetism a little more difficult to deal with mathematically, is that fundamentally the force, the magnetic force, is based on a cross product. Now, cross product is nothing new to us. Magnitude of the first times magnitude of the second vector times the cosine of the angle between the two, and the right-hand rule gives us our cross product direction. So there's nothing new with cross product, but we have to do it every time we want to calculate the magnetic force. Notice, and I'm up to my notation here at the top of the page, because it is important for you never to lose sight of the fact that always, because of the cross product, always the magnetic force will be perpendicular to the QV vector and the B vector, because it's perpendicular to the plane of those two vectors based on our right-hand rule and our cross product. So when we did QV cross B, our thumb points in the FB direction here, and notice it's perpendicular to the plane, so it's perpendicular to the V vector and to the B external vector. We'll see that the magnetic force always being perpendicular to the V vector definitely has consequences for what that force can and can't do, and we'll get to that in a moment. But let's first finish our discussion of cross product, and we're going to practice and remind ourselves and get back into cross product mode very quickly here. Well, in our first kind of reminder of what cross product does and gives us is it gives us a max and min situation. So we get a maximum magnetic force when our cross product QV cross B is big. So if the particle that we inject into the magnetic field is is heavily charged, right? So a lot of charge, then you'll get a large force. If it's moving very fast, you also will get a large magnetic force. If the external field itself is a strong external field, you get a large force. And notice that we also get the largest magnetic force, right? FB max will occur when the particle is injected itself at 90 degrees to the V vector and the B vector. And again, we're going to do actual calculations and get more comfortable with this as we go along. But these are all things that we have to keep in mind right up front, and it definitely makes it a little more challenging to get started to set up the magnetic force in terms of how it will affect the charges that are injected into it. And of course, the angle in our cross product, last part of my notation here, I kind of skipped over, is you draw the vectors from a common origin, and then of course then you take the angle between them is 0 to 180 degrees. And our final part of this introduction to QV cross B is when we have a small magnetic force or no magnetic force. So FB min will occur when you're injecting a particle that is weakly charged. And if it's neutral and has no charge, then notice there's no magnetic force. If you inject the particle with very little speed, very slowly, you get a very small force. And if you just place it in the magnetic field and it's not moving, you get no magnetic force. Well, I would hope it makes sense that if the magnetic field that you're injecting it into itself is weak, right? So the B external is weak, you'll have a small magnetic force. And notice that if you inject the particle so that Q is either moving parallel or anti-parallel, you get no magnetic force. So if a charged particle could actually talk, it would tell you that it doesn't see a magnetic field at all. It doesn't know that there's the existence of a magnetic field if it's streaming with the magnetic field lines or against the magnetic field lines identically. So you are going to now practice and review your cross products by looking at some questions here using the right-hand rule. Consider the B field to be in the plane of the page and the V vectors also to be in the plane of the page. So what you're going to do is do QV cross B. So you are going to calculate FB for each of these 4 situations. You are going to use QV cross B. And the last thing you need to know is that when you take your cross product, we are using the convention that the charge that's moving is a positive charge. If it's a positive charge, we do QV cross B as we would normally do our cross product. If the problem that you're given, it's actually a negative charge, like it will be down here, you simply reverse your thumb by 180 degrees, and that will be the direction that the magnetic force goes in. So take a look at this, draw in the B vector with all of these V vectors from a common origin, draw them from a common origin. You take QV cross B, where the angle will be between 0 and 180, and see if you can get the magnitude of the force and the direction with your right-hand rule and your thumb. In this case, it will either be coming out of the paper or into the paper based on whether it's a positive Q, where you leave your thumb direction the same, or a negative Q, where you reverse your thumb direction. And we will talk about this in class as well. But if you pause the video right here, attempt them, and when you unpause, I will show you the solution. So go ahead and pause. Okay, hopefully you've attempted all of these at this point, and I'm just going to put the solutions here for you. You can pause the video again and look at them, and we will go over these solutions in detail in class if you have questions about how the answers are the way they are.